In this video, I'm going to show you how to implement a neural network with one neuron only by utilizing arithmetic operations and pure Python. So we are not allowed to import any kind of third-party libraries. In order to create a neural network with one neuron, we have to have only one input and one output. So our input could be anything, but I just set it to 0.3, and we also require only one weight. Weights are initialized randomly, but we cannot use any kind of library. That's why I just set it to 0.4. And we also require a target, which is our desired required value from our neural network. So it could be 0.9 or whatever. Here, I'm gonna calculate the output of our neuron, which is input multiplied by weight. Here, the weight updates itself in such a way that by multiplying itself with input, the output of this multiplication become something near or similar to the target. That's a pretty powerful tool to manipulate input in such a way to make the error function, basically the output of our neural network, becomes similar to the target. After calculating the output of our neuron, we are going to calculate the error of our neural network, which is the difference between the output and the target squared. We call this mean squared error. We use this squared because it makes the error positive, so we don't have any negative numbers, and also it is numerically more stable, because once the error is small, the step size is small as a consequence, and once the error is large, the step size is also large. After calculating the error of our neural network, we are going to update weight in such a way that the error goes down as far as possible. We can use optimizer algorithms such as gradient descent to find the minimum or maximum of a function. Here we try to use gradient descent to find the minimum of our error function with respect to x. So we are going to update x because we are not allowed to update input or target. So what we are going to do is use gradient descent to find the minimum of our function, which is this one, which is basically our neural network. Okay, so I defined a variable named gradient to calculate the gradient of our function with respect to weight, which is 2 multiplied by the difference between output and target multiplied by input. This is basically the derivative of our function with respect to weight. If you are not familiar with derivative rules, you can simply give it a search, such as derivative rules, cheat sheet, or something else. And you can also use simulab.com or other websites to calculate the derivative of a function automatically. For instance, here our function is x multiplied by b. X is our weight and b is our input, minus t, which is the target, squared. Yeah. So as you can see, the derivative is 2 multiplied by the difference between the output and the input multiplied by b, which is our input. Okay. After calculating the gradient, we are going to use that gradient to update the weight. We call this a step size, and in deep learning we also name it learning rate. What does that mean? That means that we only use 80% of our gradient to update weight. Okay, let's just see this in action. What we have done is weight, the actual weight minus 80% of our gradient. Okay, we are updating our weight. Here, as I said, an optimizer algorithm such as gradient descent can work with any kind of function if we can calculate the derivative of the function, or basically the function is differentiable. So here our function is this one. Suppose that this function is our error function and the minimum of the function is at this point, 0.79. And this one is the derivative of our function, which is the blue line. As you can see, as the function goes down, the gradient is negative. And near this flat space, the gradient is 0. And as the function goes up, the gradient is positive. Okay, so let's just see one step of gradient descent in action. So our weight is -1. The output is 6, which is our error value. And we want to find a suitable weight value that makes our error value much less than this. Okay, what we are gonna do is calculate the gradient at point -1, which is -6. We use gradient at point -1 to update our weight value. -1 minus step size multiplied by the gradient at point -1 is just the update or the next value for the weight. Okay, we gave the next value to the f in order to see the error value. As you can see, the error went down from 6 to 3.82, and also our weight went down from -1 to -0.4. So that's perfect. We just managed to reduce the error from 6 to 3.82 with only one step. Okay, but please observe that do not use a big step size, for instance 5 here. As you can see, that the next weight value became 2, which made the error almost double, and it made everything worse because our step size is quite large and it jump around the flat area. Okay, that's why we require to use a suitable value as a step size or learning rate. Okay, let's just get back to our code. Let me just print the output and the error of our network. And let's observe the behavior of the model with one iteration. Okay, the output is 12 and the error is 0.6. Let me run it with another iteration. 23, 32, 41, and as you can see, the output is approaching to the target and the error is going down. So let's just run this code for a couple of more steps. The output is approaching and the error is going down. Remember that it's never gonna be precisely equivalent to the target. It's only approaching, And as you can see, the error is pretty small. And once the error is pretty small, our update is pretty small too. So the weight won't change much. And these are perfect properties of neural networks. That's enough for this video. I'm going to show you how to use activation functions. In the next video, activation functions help neural network to learn complex tasks. We are going to also implement a couple of variations of this code. The next video is going to be interesting because we are going to add a couple of more features to our simple neural network.